All right, let's dive right into this explainer. Today, we're looking at exactly how artificial intelligence is completely revolutionizing skin cancer detection. We're going to unpack a really fascinating new architecture and figure out how to balance that cutting-edge tech with the real-world clinical ethics we need to actually use it safely. Here's the roadmap for today. We're going to hit the skin cancer challenge, AI's promise and pitfalls, the DermaMamba breakthrough, peek inside its dual architecture, touch on human and AI collaboration, and finally, wrap up with the ethics of AI dermatology. Starting with Section 1, the skin cancer challenge. To really grasp why this new tech is such a big deal, we first got to look at the sheer human cost here. Take melanoma, for example. It makes up only about 1% of all skin cancer cases, but, and this is a staggering statistic, it's responsible for a devastating 75% of skin cancer-induced mortality. The stakes are literally life or death. Catch it early and survival rates are over 99%, but if it's caught late, that number just plummets. And looking at the current screening workflow, it's incredibly intensive. You go from the initial risk assessment to visual exams, down to dermoscopy, and then finally a biopsy. But here's the real kicker. Even the most expert dermatologists only hit about 60 to 80% accuracy when evaluating really complex, ambiguous cases. Human eyes, even highly trained ones, just have their limits when trying to tell apart benign and malignant spots that look almost identical. Moving to Section 2, AI promise and pitfalls. So bringing AI into this workflow looked super promising at first, right? But it came with some pretty massive technical roadblocks. For years, the field was basically split in two. On one hand, you had convolutional neural networks, or CNNs. Think of a CNN like looking through a magnifying glass. It's awesome at spotting tiny local details, like a jagged border or a weird color shift, but it completely misses the big picture. On the other hand, you had vision transformers. These are fantastic at seeing the whole image and grasping the overall context. The catch? They need an insane amount of computing power. They scale with quadratic complexity, which basically means as the image gets sharper, the computer power you need just skyrockets. Standard hospital computers literally couldn't handle it. Which brings us to Section 3, the DermaMamba breakthrough. Let's see how this brand new architecture actually solves those past failures with a really elegant solution. So DermaMamba uses something called state space models, specifically the Vision Mamba architecture. The real magic trick here is linear complexity. Instead of your computing needs blowing up quadratically as the image resolution increases, the computing time just scales proportionally. What does that mean for us? Well, it means it can crunch incredibly high-res medical images at lightning speed without melting the hospital servers. It gives you that big picture view of a transformer, but at a fraction of the computational cost. And the numbers are just wild. When tested on the massive ISIC dataset, DermaMamba hit a 92.1% accuracy. It basically blew past the best baseline models out there, all while running 2.3 times faster and using 40% less memory. That exact combo, super high accuracy and incredibly low computational cost, is exactly what we need to actually deploy this in real-world clinics. Let's crack it open in Section 4, inside the dual architecture. To see how it pulls those numbers off, we gotta look under the hood at its two-branch design. I really love the doctor's eyes metaphor for this. DermaMamba literally splits the workload down two different branches. The CNN branch acts as your magnifying glass, zooming in to intensively scrutinize localized textures, borders, and pigmentation. At the exact same time, the VMamba branch acts as the step-back view, assessing the overall symmetry and spatial context of the entire lesion. Then, a dynamic fusion mechanism intelligently weighs both inputs to make a final call. Kind of exactly like how a doctor weighs the micro and macro details during an exam. And get this, what's really fascinating is how the developers baked actual medical knowledge right into the math. It doesn't just blindly scan pixels. It mathematically mimics a clinical exam with multi-directional scanning, like doing spiral and radial sweeps over the image. It even embeds the classic ABCDE rules, asymmetry, border, color, diameter, evolution, straight into its learning process. How cool is that? Zooming back out, we hit Section 5. Human and AI collaboration. Because the big practical question is, how does a doctor actually use this thing in their office? Look, the goal here isn't to replace your dermatologist, it's to give them supervision. And the data completely backs this up. Studies have shown that when clinicians get AI-based probability support while they're evaluating a patient, their specific diagnostic accuracy jumps massively, from about 55.6% all the way up to 75%. That means doctors are confidently catching more cancers early and, just as importantly, saving thousands of people from having to get painful, totally unnecessary biopsies for benign spots. But hold on, before DermaMamba actually shows up at your primary care doctor's office, it has to clear 3 massive hurdles. First, widespread clinical validation across diverse, real-world populations. Second, system interoperability. Basically, it has to actually talk smoothly to the clunky electronic health records hospitals already use. And third, patient acceptance. Studies show 60% of patients are worried AI is going to dehumanize their care. So to move this from some mysterious mathematical black box to a trusted clinical partner, we're going to need a ton of transparency. Which tees us up perfectly for Section 6, Ethics in AI Dermatology. We really have to talk about biases and disparities here, because we have to face a pretty dangerous reality. If algorithms are trained mostly on datasets of light skin tones, which unfortunately historically many have been, they are naturally going to fail patients with darker skin. A recent study using the diverse dermatology images dataset exposed exactly this. State-of-the-art AI models showed considerably lower accuracy on dark skin tones. This isn't just a glitch, it's an algorithmic bias that can literally cost lives through misdiagnosis or delayed treatment. So how do we fix it? The path to equitable AI takes real, intentional, systemic change. Developers and clinics have to commit to diverse, multi-ethnic training data. We need strict regulatory oversight to establish clear accountability when an AI inevitably makes a mistake. We have to shift away from black box models so we can see exactly why an AI flagged a lesion. And finally, we definitely need specialized training for the primary care physicians actually using these tools on the front lines. Ultimately, breakthroughs like DermaMamba prove that, yeah, we absolutely have the raw computational power to revolutionize skin cancer detection. But the true test isn't just about getting a high score on algorithmic accuracy. As AI learns to see the microscopic details that we miss, the real question is, will we build it fairly enough to actually trust it? Thanks for joining me on this explainer, and stay curious.